Hello and welcome to this latest instalment of Texas Instruments VCE Mathematical Methods revision series. And in this webinar this evening, we will look at exam style questions on probability. The webinar theme is to try and exploit the technology to illustrate a number of possible solution methods that you have available. The VCAA have stripped back the syllabus for 2020, which is a good move. And so you will be asked to study the normal probability distribution and the binomial probability distribution. So we will try and look at a couple of question types from both, and also try and illustrate that one of the applications of TI-Nspire, the notes application, could indeed be a very good friend of yours in the exam. First of all, there were earlier webinars that were excellent, conducted by my colleague Hayley, and she went through concepts involving the normal and binomial distribution. My focus this evening is more on the machine and answering exam questions, so I won't be able to say too much about the conceptual basis behind these distributions. First of all, what we see here is a normal probability density function. Notice that it's symmetrical about the mean. It's also symmetrical about the mode and the median. Notice that it's non-negative, that the function f of x, which is that red curve there, is above the x-axis. And also note that the total area under the curve is equal to 1. The shaded area there is the corresponds to the probability that random variable capital X lies between A and B. When you're answering exam questions involving the normal distribution, it's an extremely good idea, no matter whether you're in multiple choice or in the extended response section, to always draw a diagram to help you work out what's required in the question. Also, what you could do is exploit the symmetry of the curve. For example, we know that for a normal distribution, that the probability of random variable capital X lying between the mean and 2 standard deviations, or mean minus 2 standard deviations, and the mean plus 2 standard deviations, is very close to equaling 0.95. And so situations like that can be exploited when answering such questions. So let's have a look at a typical question here. This is one from the worksheet which accompanies this webinar. So the weights, W kilograms of salmon at a farm, can be modelled by a normal distribution with a mean weight of 3.1 and a standard deviation of 0.4. You're asked here to find the probability that a randomly selected salmon from the farm will weigh less than 2.5 kilograms. I've highlighted less than. When you're answering probability questions, it's important that you get the phrases right. So less than, more than, at least, at most, etc., etc. What you need to do is you need to turn those into probability statements, which I've done here. In other words, we want to find the probability that random variable capital W is less than 2.5. Also note here that we're asked to specify our answer correct to 4 decimal places. So let's have a look at our solution. I'm in a notes page or a notes application at the moment. And what you see is a series of math boxes, which are objects that are housed in a notes application. To enter or to insert a math box, you press Control M. And here is an example of a math box. And the input is in blue and the output is in green. And what I'm attempting to show you here is that if you set up such pages, then you can use them in the exam to hopefully answer such questions accurately and efficiently. There will be an upcoming webinar on setting up such pages run by Chris Ison, so make sure you look out for that. So what I've got here is I've got mu. Now this command here is the assign command. It's colon equals, and it would be accessed by pressing Control and then the symbols template. It works like define essentially. So our mean is 3.1. You cannot unfortunately use the Greek letter sigma, so you've got to use the word. So I've assigned mu to be 3.1, sigma to be 0.4. We want to find the probability that random variable capital W is less than 2.5. So we've got our left tail goes all the way out to negative infinity. So we've got an A value of negative infinity. We've got a B value of 2.5. And I've got this mysterious DP assigned to be 4. DP stands for decimal places. So what we can do is we can, in this math box, exploit the use of the round command. So we're going to round, we're going to use the normal CDF, which is our command which enables us to calculate probabilities. So in other words, we're working out the area under the curve from negative infinity up to 2.5 for a mean of 3.1 and a standard deviation of 0.4. And we want our answer to 4 decimal places. And what would happen there is we get an answer of 0.668. If you're a decimalizer and you like to round yourself, this is the corresponding math box underneath that doesn't have the round command. So, for example, you might want to, or you come into the exam and you get a question. Lo and behold, it has the same mean and standard deviation, but it says, find the probability that a random selected salmon from the farm will weigh less than, say, 2.8 kilograms. Well, this is how the dynamic and interactive nature of notes pages work. So instead of 2.5 for B, we go into the math box and then we press delete to remove the 5, change it to an 8, and then what I want you to do is I want you to watch these two math boxes here when I press enter. And when I press enter, what you get is you get an updated probability. So if the question asks for finding the probability that random variable capital W was less than 2.8, then correct to 4 decimal places, that answer would be 0.2266. I'll change that back to 2.5, press enter, go to the next page. Here is a graphical representation of what's going on. What I've done is in the function entry line, I've said I want to graph the normal probability density function, norm PDF. I want to do it in terms of X, and my parameters are mu and sigma. And when I do that, what happens is I get that blue curve. So what I've done here is I've constructed a segment which represents B, and this value here represents that shaded area. So that shaded area there is the probability that random variable capital W is less than 2.5. We go back to the previous page and we change 2.5 to 2.8, and then we go to the corresponding graph page and it's updated for us because we're within the same problem. All right, so our segment has changed, our B value has changed, and so that shaded area is the probability that random variable capital W is less than 2.8. So that illustrates the interactivity between pages. It also shows you a graphical method of solution. And again, we're going to come back to this, that there are quite a number of different ways that can be exploited to solve these questions in exam conditions. And what you've got to do is, in consultation with your teachers, work out the most efficient and accurate approaches. Moving right along, let's have a look at the opposite type of question, the inverse normal distribution. So for a standard normal distribution, to find a particular value Z, if the probability that random variable, which is a standard random normal variable Z, is less than Z is equal to P, what you do is you use the inverse normal command, so it's innorm P. So here is an illustration here. So the area to the left of Z is 0.67. What's the approximate value of Z? Now what you can see there is, because we're dealing with a standard variable, we know that the mean's equal to 0. So we would expect a value of Z to be greater than 0. So when you draw diagrams and they're clearly labelled and you know exactly what you're doing, also think about what sort of answer might you expect. If you went back here, for example, and we've got a mean of 3.1, and we're finding the probability that random variable capital W is less than 2.5. 2.5 is less than the mean. Now, the area to the left of the mean is 0.5, so we would expect our answer certainly to be less than 0.5. So ask yourself, what sort of answer do I expect when I'm answering a question? The best students seem to be able to do that. For a non-standard normal distribution, to find the value of x, for example, such that the probability that random variable capital X is less than x equals p, for example, use inv norm of p. Okay, so let's have a look at an inverse normal example. And this is one from the worksheet. So again, we've got our salmons, our salmon farm. And according to this model, 99% of the salmon weigh more than W kilograms. Find the value of W. So this is a situation where we've got to, first of all, highlight more than, and also work out what this 99% of salmon weighs more than W. What does that mean? So what we do is it's called mathematizing. It's taking words and turning them into mathematics. So what we want to do is we know that 99% of the salmon weigh more than W. So what's W? So we're expecting W to be less than the mean, certainly, because the probability that random variable capital W is greater than W is equal to 0.99. And exploiting the symmetry of the normal distribution curve, that is equivalent to the probability that random variable capital W less than W equals 0.01. Okay, so that's the way that the inverse normal command works. It works leading up to that 0.01. So I know this might give the answer away, but here is the situation where that is going to be, that's our critical value, W, and 99% of the salmon weigh more than that value. So we'll discuss how this is calculated by going back to the previous page. And again, I'm exploiting a notes page here. So again, we've got a mean of 3.1, a standard deviation of 0.4. The question asks us to express our answer correct to 1 decimal place. So that's why I've got DP1 assigned to be equal to 1. Because I'm in the same problem, back a couple of pages, I had DP assigned to be 4. And if I had this as DP, then this would be assigned to be 4. So that's why I've changed variables there. So what we've got here is we've got everything set up, and then our W value is going to be using the inverse norm command, and the syntax is our P value, which is 0.01, our mean, which is 3.1, our sigma, which is 0.4, and our decimal places, we want it to 1 decimal place. So we get an answer of 2.2 kilograms correct to 1 decimal place. Alternatively, what you can do is you can assign K to be the inverse norm of P, and that value there, negative 2.32, that corresponds to how many standard deviations that weight is below the mean. All right, so it's 2.32 standard deviations to the left of the mean. And what you can do is using your transformation equation, transforming between x and z, you solve. I've called it W1 minus mu. So this is essentially W1 minus mu on sigma equals the inverse normal of P. Solve it for W1, and you get that W1 value of 2.16, etc. Rounded to 1 decimal place, that's 2.2. So these are the same. This is correctly rounded, and this contains the decimal places. You can also do a check, actually. We can I've called this WC, C for check, and to put that in for P, mu and sigma 2.16, and then the normal CDF from negative infinity up to WC with the correct values for mu and sigma gives 0.01. So that checks out really nicely. Now, for example, if we had a different question, and let's say it said, according to this model, 95% of salmon at the farm weigh more than W kilograms, then what we would do is we would change 0.01 to 0.05, and we would press enter, and we get a corresponding update for all our linked math boxes. So in that instance, the value for W would be 2.4 kilograms. And I have this page linked as well. So notice that that area is now 0.95, and that critical value or value for W, correct to one decimal place, is 2.4. So again, if I went back here and change this to 0.01 and press enter, there we go. So it's updating as the math boxes change. The other thing that I want to show, now this might take a couple of minutes. It's a little bit, well, see what you think. I've got here window setting of 1.1 to 5.1. Now you mightn't realise this, but you can set that up in terms of mu and sigma. So I've got that as mu minus 5 sigma and mu plus 5 sigma. So I'll just show you how that works by jumping out of the document and going to just a blank document where, for example, I'm looking at the standard normal curve. So I've assigned mu to be 0 and sigma to be 1 on a calculator page. And then I go to my graph page. Now, I've already set this up. That's mu minus 5 sigma, and that's mu minus 4 sigma. If I click on this twice and then go in there, and then if I press the catalog button, go into my symbols and choose mu, you can tell that I've done this before, and press enter, and then minus 3 times sigma, and press enter, that -5 should change to a -3, which it does. And then over here, click on that a couple of times, and then delete that, and then we've got mu plus 3 sigma, and you get 3. So that's a way, actually, of setting up a viewing window in terms of your parameters. This is set up nicely because we've got the standard normal variable. I know we don't have a curve there, but we would expect it to be symmetrical about that vertical axis. Okay, moving right along. I think I'll skip over a bit of this next problem and just show you some different features, but let's get a handle upon what the problem's about. So Catherine qualified to compete in a javelin throwing comp, and in training for the comp, the distances thrown by Catherine were found to be a random variable, capital X, and are found to be normally distributed with a mean of 59.5 and standard deviation 3. Excuse me. The first part asks us to find that probability. We've already done that, and here is our math box setup, and that's what you would do there. Go to the next page. This one's with conditional probability. So let's find the probability. So conditional probability is about a reduced sample space. So in terms of the normal distribution curve here, the condition is that we want to find the probability that Catherine throws at least 63 metres, given that she's thrown 59.5 metres. Now, the mean's 59.5 metres. So what, in effect, we're doing is we're reducing the sample space to the right-hand half, if you like, of the normal distribution curve. So when we apply conditional probability considerations, this probability is equal to the probability that X is greater than or equal to 63 intersection and X is greater than or equal to 59.5, on the probability that random variable capital X is greater than 59.5. Now, we should in our heads know that the denominator is going to equal 0.5. Now, you mightn't need this, but be aware that your Nspire will work out equations involving intersections. So here I've asked it to solve, bear with me here, that these should be random variable capital X, but when you press enter, uppercase becomes lowercase. So just bear that in mind in terms of notation. So if we solve random variable capital X greater than or equal to 63 and random variable capital X greater than or equal to 59.5 for X, we get random variable capital X is greater than or equal to 63. Now, you shouldn't need to do that calculation, but it's there for you if you want to. If we go out into our document here again, here is an example of what's going on in a calculator page. For example, if you wanted to work out the interval such that X was less than 120 and X was greater than or equal to 90, when you solve that for X, you get that X lies between 90 and 120. It includes 90 and doesn't include 120. So what we've got is we've got a reduced sample space. So really it's this probability divided by 0.5. And so we've got our math boxes set up for mu, for sigma, for our A value, our B value. So, you know, the lower limit there, 59.5, the upper limit there, 63, 4 decimal places. And so this math box here, we're using the round command again. So if we change DP from 4 to 3, that would give us a 3 decimal point answer. So this is the conditional probability put into machine or to TI-Nspire notation. And so the numerator is the probability that X is greater than or equal to 63, right? Because that's the intersection, that's the numerator. The denominator is the probability that random variable capital X is greater than or equal to 59.5. And when we employ that calculation or do that calculation, we get 0.2433. Okay, moving on. Often what happens in exam 2 is there's questions that might start whereby you're looking at the normal distribution, and then you're asked to use that and look at a situation which is governed or described by a binomial distribution. So in this competition, javelin competition, Catherine has 5 throws. Use Catherine's training model to find the probability that at least 2 of her throws will be at least 63 metres. Give your answer correct to 4 decimal places. So I've set up another page here. She has 5 throws, so N is assigned to be 5. This is our probability, and here where this is the probability that random variable capital X is greater than or equal to 63. Our lower value or our lower limit is 2, because we've got at least 2. So at least 2 throws means 2 or 3 or 4 or 5. So we've got a lower value of 2 and an upper value of 5. 4 decimal places again, so DP has been assigned to be 4, and then using the round command and then not using the round command, they are our probabilities. Let's say that the question changes and that in the competition, Catherine actually has 10 throws find the probability that at least 4 of the throws will be at least 63 metres. So we change 5 to 10, and we'll just scroll down a bit, press enter. Notice that number changed. Now I said probability that of at least 4. So we have a lower value of 4, press enter. Upper value of 10, press enter. All right, so that's for 10 throws. The probability that at least 4 of those throws go 63 metres. So what you do Again, I want to reinforce that you set these notes pages up in consultation with your teachers and fellow students in the exam beforehand, and then go in and use them. So you still have to understand what the question's telling you, and then you've got to employ the notes page to answer the question. The other thing is be really careful about the way that you set out your working. And I might talk about that in the next example. Make sure that you use correct mathematical notation, symbols and conventions. I would stress to students to write down what the distribution is. So if X is a binomial distribution and you know that N is 10 and P is 0.4, then I would write X is a binomial distribution with N equals 10, P equals 4. And if you wanted to work out, say, the probability that X equals 3, I would write PR, open bracket, X equals 3 equals the answer. And that should be sufficient working. Your TI-Nspire also has an inverse binomial command. And so the probability of a target shooter hitting a bullseye on any one shot is 0.2. Find the least number of shots the shooter should make to ensure that a probability of more than 0.95 of hitting the bullseye at least once. So find the least number of shots, so the least value of N, the shooter should make to ensure that a probability of 0.95 of hitting the bullseye at least once. These are not easy questions to get your head around. First of all, work out that you need to be finding the value of N. Also note that your probability of success P is 0.2. And also, as soon as you can, try and work out what random variable capital X is. Random variable capital X is the number of bullseyes. So we want to work out or look at mathematizing this statement and turning it into mathematics. So the probability that random variable capital X is at least 1, greater than or equal to 1, is greater than 0.95. And that is the mathematical probability statement that we glean from the wording of this question. And what we want to do is we want to use this to find the value of N, the least value of N. Now, at least 1 is the same as 1 minus the probability of X equals 0. So we can write this inequality as 1 minus probability that X equals 0 is greater than 0.95. Then what we can do is we can subtract 1 from both sides and divide by -1, which will change the sign of the integral, the inequality sign, the inequality sign. And so what we're after is our final statement before going to the calculator is the probability that X, random variable capital X, less than or equals 0 is less than or equal to 0.05. And we want to find the value of N that satisfies that. So C-prob is a cumulative probability, and it's been assigned to be 0.05, and you can see why. The probability of success is 0.2, and the value that random variable capital X takes is 0. So they are set up there. Now, our next math box, this is using the inverse binomial command. And so if you're using it in a calculator application, what will happen is you'll get a field to fill out. And so in the first field, you would write 0.05. Then your probability value is 0.2. But here you don't need to write them out because they've been picked up from these earlier math boxes. X is 0. This 1 is like a binary counter, and it is telling the calculator, I want to write this as a matrix, and I want to see the last incorrect N value before I see the correct N value. So here we see our matrix. So when N equals 13, the cumulative probability, or that probability, is 0.054. It's greater than 0.05. So N can't be 13. We want to find the first N value such that that probability dips below 0.05, and it does so when N equals 14. Okay, so the least value of N is 14. If you don't want to use the matrix, then all you need to do in this math box, I said it's binary, it can either be 0 or 1. So with a 1, it's a matrix, and with a 0, it's not. And what you get there is you get your answer of 14. A more off-the-wall approach is you can define the binomial distribution in terms of its parameters np and x by its formula, NCR. So this is really n choose x times p to the x times 1 minus p to the n minus x. So once that's assigned, then using the p and x values, basically this comes down to solving the inequality 0.8 to the power of n is less than or equal to 0.05. And so when you do that, you get n is greater than or equal to 13.42. N is an integer. We don't take the 13, we take the 14, and that's spelled out by that matrix there. So the matrix is actually quite instructive. Moving along. Here is the same example done with a function table. So I'll show you this one, possibly one more example, and I expect to finish in about another 7 or 8 minutes if that's okay. So this is the same example, the same mathematics, same p-value, and what I've done here is I've assigned f of x to be the binomial probability mass function, it's actually called, of x, p, and 0. So here, I have to use x when I'm graphing and using the function table. It's actually n, all right? So that's actually n. That's p is 0.2, and that's corresponds to that 0 there. Go to the next page. And so if I press tab, this is what I graphed. I graphed that assigned function from page 5.1. And if I press Control T, what will happen is that you'll get a split screen and the table will appear. And so this is a table. Down the column 1, these are all n values, right? We have to use x because we're graphing, right? So these are all n values. And these are all probabilities that random variable capital X equals 0. And what we want to do is we want to scroll down the table to find the first value that dips below 0.05. And there it is, all right? So there's your 13 from, if you remember your matrix, is a probability just above 0.05. And there's one that's just below 0.05, all right? So in other words, the least value of n is 14. So that illustrates, again, another possible solution approach. This one's quite straightforward. This one uses not the inverse binomial n command, but the inverse binomial command. You can find all these under probability and under distributions. So given that random variable capital X is a binomially distributed variable with n equals 10 and p equals 0.2, should that be 0.2 or 0.28? If I have a look at my, let's say it's 0.28. Okay, let's say it's 0.28. And the probability that random variable capital X is less than or equal to k is 0.9658. So what I want to do is I want to marry up the question with the math box here. So n equals, right, so given that, we want to find that. Okay. So our probability is 0.8. Our cumulative probability is 0.9658. And what we do is we use the inverse binomial command. And when k equals 4, you see that that doesn't match up with that probability. But when k equals 5, it does match up with that probability. So in that instance, the probability that x is less than or equal to 5 is equal to 0.9658. So in other words, that's summing up the probability that x equals 0 plus 1 plus 2 plus 3 plus 4 plus 5. And what you'll also notice is that in this instance, n is not playing a role. So when I send this file so that you get it, I'll remove that math box. Our final example for the day is a typical question where you've got a normal distribution. You're given two probability statements, but the mean and the standard deviation are unknown, and you want to find the value of mu and of sigma. So what we want to do is we want to turn these probability statements into structured math boxes. So I've said that I'm going to assign x1 to be 30, and I'm going to assign p1 to be 0.4. And I also want the corresponding inverse normal value of P1. So that's K1, and that's 0.25. Then do exactly the same with the second probability statement. X2 I'm going to assign to be 55. P2 is 0.9, and K2 is the inverse normal of P2, and that's 1.28. We're asked to find our value for mean and for the mean and the standard deviation correct to one decimal place. So DP has been assigned to 1. Now I've used the zeros command here, and I'll also show you the solve command in a math box below. So I've wrapped it around the round command. So we're getting answers correct to one decimal place. And so we see there that our mu is 34.1 and our sigma is 16.3. I used S because I didn't want to use sigma, and I can't use sigma the letter. These equations are assumed to be set to 0, all right? So they're assumed to be set to 0. When you're writing these out on your exam paper, don't write it in machine language, write it with correct mathematical notation. If you're not keen on using the zeros command, here's a corresponding math box using the solve command. And so here we're solving those two equations for mean, for mu, and for the standard deviation. And we get standard deviation and we get mean to be those values. So that all corresponds nicely. And the last thing that I want to show you today is that this can also be done graphically. So what I've done here is if you press tab, press escape and press tab, what I've done is I've used the relation command, the relation graphing, to graph these. So I've written this as 30 minus x equals y times inverse norm of 0.4, which I think is P1, and 55 minus x equals y times the inverse norm of P2, which is 0.9. Now, I tried this by writing 55 minus x on y equals inverse norm of 0.9, but the calculator didn't accept it, all right? So that's why I've written it in that form. Press escape. And what we're basically doing is we're solving two equations, two unknowns, and they're straight lines. So you can graph them and find their point of intersection. So that's what I've done. And the coordinates of the point of intersection there is 34.1 and 16.3. So that's the mean, and that is the standard deviation. So be aware that such questions can also be solved using a graphical approach. Okay, I think that might be a good time to wrap it up. So again, kudos to the VCAA for stripping back the probability syllabus so that you only need to study the normal distribution and the binomial distribution. Practice lots of questions. Set about setting up some notes pages to help you with the most popular question types. So study past exams, work out what are very popular question types, set up some notes pages, check that they work. So check them on a few different questions, check them with your teacher, share them with your teacher, and hopefully, and specify your solutions with correct mathematical notation. I think that's all. So good luck for the rest of your studies and the lead up to the exams and the exams. Using the notes pages should be able to give you a pretty good head start with a few of the most popular question types, and should hopefully improve your final score at the end of the year. So good luck. Thanks very much. Good evening.